When we model complex systems over extended timeframes, we eventually hit a limit. We can map immediate reactions and short-term cycles, but defining a system's ultimate conclusion often forces us to guess. We might assume a degrading structure simply vanishes, or we might try to stretch our short-term narratives infinitely forward. Both approaches break the mathematical rigor of the model. The Unified Harmonic Systems Framework rejects this guesswork. In UHS, the long run is not a measure of time. It is a strictly defined set of operationally testable behaviors. If a framework lacks mathematically enforced limit constraints, any claim about where a system ends up is indistinguishable from speculative fiction. Chapter 12, titled Return, provides the mathematical architecture that closes the technical arc of the entire UHS framework. To function, this chapter requires a specific intake. It receives the finalized system descriptor bundle handed down from Module 11. This bundle contains the system's compressed aggregate structure, as well as its retained history across multiple separated episodes. Chapter 12 exists to test this bundle against the absolute limit constraints of the continuum. By doing this, we transform descriptive historical data into a predictive, mathematically testable destiny. This visualization shows that long-run trajectories do not branch gradually. They diverge based on hard geometric gates within state space. The first path is the return stable class. Here, the state remains admissible and converges into a stable, continuum-compatible arrangement. The second is the cycle stable class. The system remains strictly admissible while looping in bounded orbits that are consistent with its past history. The third is the drift-managed class. The state moves across different trajectory classes, but it remains governable and contained within our declared intervention authority. The final path is the boundary loss class. The state leaves the admissibility envelope entirely, immediately invalidating any prior claims of stability or closure. Notice that these branch points are objective, mathematical gate crossings. They are not cosmetic variations in the system state. A system's ultimate survival or failure is dictated by these exact geometric thresholds, regardless of how much time passes. These trajectory classes allow us to define the asymptotic regime. This is the operational region where a trajectory ultimately settles as time approaches infinity. This diagram maps the attractor basin, denoted as script B. This is the geometric zone of safety where the system remains stable and intact. The absolute boundary of this basin is the separatrix. Crossing this separatrix marks the mathematically defined transition to irreversible boundary loss. When this happens, equation 1201 dictates that the boundary loss entropy leaking from the system is exactly equal to the renewal influx drawn from the continuum. The separatrix draws a precise line between survival and dissolution. It proves that the continuum acts as a generative reservoir, perfectly absorbing the structural loss. To put these limits to use, we test the system using comparative scenario analysis based on explicit policy controls. This split-screen diagram establishes our parameters by holding the initial configuration, our psi state, completely fixed across two scenarios. Path A applies a policy control that prioritizes short-term throughput over stability. The system runs faster, but the trajectory swings outward, breaching the separatrix and failing. Path B applies a policy control that strictly prioritizes admissibility. The output is lower, but the system locks into a cycle-stable orbit safely inside the basin. In UHS, ethical constraints and governance hierarchies are treated as hard mathematical model contracts. If a proposed intervention increases the probability of boundary loss, governance rules block it during the pre-intervention review. Preserving admissibility strictly outranks temporary efficiency gains. By counterfactual testing against the separatrix, we guarantee long-term safety, enforcing structural stability over raw output. This brings us to the ultimate theoretical question. When a highly structured system finally crosses the separatrix and dissolves, where does its structural information go? To answer this, we define closure claims. In UHS, a regime is considered closed when we do not need any unresolved outside mechanism to explain its behavior. This equation outlines the proof of asymptotic completeness. The total state space equals the bound state space plus the reservoir state space. The bound basis represents our complex system undergoing dissolution as it drifts across the separatrix. As it breaks apart, the information strictly transitions into the free continuum states, the reservoir basis, without a single data point vanishing. Dissolution functions strictly as a zero-loss, thermodynamic and informational phase transition from a bound structure back to the generative continuum. Chapter 12 finalizes this process with a handoff to Module 13, taking the form of a structured downstream diagnostic package. This package inventories the trajectory classes, records specific geometric gate failures, and updates the fragmentation risks for the system. Together, these metrics provide the minimum required intake for advanced safety and pathology diagnostics. And so, we are left with a profound conceptual view of the continuum as the ultimate uncorrupted substrate. The continuum is mathematically pristine. Emergence and dissolution are simply phase changes within a fully conserved harmonic space.